While we are still on the chapter axial loading, what we will do in this lecture is that we are going to look at a generalized form of the Hooke's law in 3 dimension, right? So if you remember from what we had looked at for the Hooke's law was that we had essentially looked at one-dimensional problems, right? So we had, say, a gauge or a wire, and we were pulling it, and from that we established the relationship that your normal stress sigma is directly proportional to the normal strain epsilon through the proportionality constant E, which was the Young's modulus, right? What we are going to do now is that we are going to look at 3-dimensional objects and see and derive a more generalized form of the Hooke's law. First, we are going to start with the only axial loading. Then we are going to spice things up a bit and we are going to look at axial as well as shear. And you will see that how the Hooke's law quickly changes from the very simple expression that you have seen to a slightly more complicated version. I wouldn't say it complicated. Once you understand, it is very easy to keep a track of the different values of the stresses and the strains and for which all cases it arises, right? So to begin with, let's look at the thing which we are familiar with, that is the one-dimensional Hooke's law, right? So if you recall what we had seen, that our sigma, right, which was our normal stress, was equal to our E times our epsilon, which was the normal strain, right? And while we were discussing Hooke's law, we also discussed one more important concept, which was the Poisson's ratio, right? Remember, the Poisson's ratio was the ratio between the lateral strain divided by the longitudinal or the axial strain, right? So if you are pulling with a force P on either ends, you have an expansion of the material along with the contraction in the lateral direction, and because they are of two opposite natures, you have the negative sign, so you had negative of epsilon prime by epsilon over here, right? Now this was a generic example. Let's introduce some coordinate axes and see that how the same expression can be written in 2 dimensions. So what you have over here is the coordinate axis x and y, and for the same bar, maybe the same bar, let me pull it now with a force P. So if I am pulling this with a force P over here, right, I will get an equal and opposite reaction at the support. And for this bar, right, I have a longitudinal strain over here, as you can tell. So this is going to have some longitudinal strain over here, which say I'm going to mark with epsilon x because it is in the positive x direction, right? And I am going to have a lateral strain. I'm also going to have a lateral strain over here, which is, remember, this is happening in the negative y direction over here. So this is going to be minus of epsilon y, right? So if I have to write the same Poisson's ratio now in terms of strains about this particular coordinate axis, how do I write it? So my nu becomes equals to negative of epsilon y divided by epsilon x, right? Simple. Now think about it. Suppose this is my member which you're looking in 2D over here, right? And say this is my positive x and this is my the positive y axis over here, and you see when I'm pulling it, right, I am having this extra strain, the expansion and a contraction about this axis, and for which I wrote this formula very easily. But in this one, is there only an x and a y axis? No, this has a third dimension as well. It has a x and a y and a z direction, right? So if I am pulling it, in addition to the contraction, you just have to visualize this. In addition to the contraction along the y direction, I would also have a contraction about the z direction as well, right? So if I have to write that this particular expression, and let's maybe look at this this example which I was showing you in terms of a figure. If I have to take a look at this one, it looks something like this over here. You have the bar, right, and you are pulling it with this force P, right, and you are having, and this force P is acting along this positive x direction, as you can see over here, and we have a positive y direction going vertically up and a positive z direction over here. So when you are pulling it along the positive x direction, along with that you are having a contraction in the y direction, you are having a contraction in the z direction as well. Now remember, this Poisson's ratio nu, right? For a homogeneous isotropic material, this is direction independent. Right? So this nu, which we had looked at, for this particular example, we can simply come and write as my nu is the same nu which we had looked at is going to be equals to minus of epsilon y by epsilon x, which we had already looked at over here, right? And this I can maybe write this a little further, that my epsilon y becomes equals to negative of nu epsilon x, right? Now in addition to the y direction, I can also write my nu as negative of epsilon z divided by epsilon x, right, to account for the contraction in the z direction. And this will further give me the relationship that my epsilon z is equals to negative of nu epsilon x over here, right? So I get two relationships over here. This is number one and say this is number two over here, right? From the Poisson's ratio by considering the contractions about the y as well as the z direction over here, right? So now the question is that if I have a structure, right, here you have those small tiny bits within the structure we are looking at, remember, right? If I have a structure with a multi-axial loading, so instead of just having sigma x, I also have a sigma y and I also have a sigma z over here, right? When I have a structure like this, or a bit of an element, a small cube if I've extracted from a structure, right? The question is that what is going to be my different strains, right? I have these stresses over here in terms of the sigmas. So what is going to be my epsilon x, epsilon y and epsilon z? And for this, we are going to use the very famous principle of superposition. You are probably familiar with this. What the principle of superposition essentially states is that once you have a structure with a combined loading, as long as you are within the small deformation limits, right, the effect of the combined loading can be expressed as a summation of the effects of the individual loading. The easiest way probably to understand that is that suppose if you have a beam, right? Suppose if you have a beam, and if I have to draw a beam over here, right? And this beam, right? If suppose I have on this beam two loads, say P1 and P2, right? And say my objective is to find that when this beam deflects, right? Suppose this is my deflected shape of the beam. When this beam deflects, I want to find that what is my deformation at the center. That if that is my objective, what does the principle of superposition state? This principle of superposition states that this beam can simply be expressed as the combined effect of two separate beams, right? For which if I have the same beam, right? In this beam, when I have this load just P1, right? And for this, if I am calculating this deflection delta at the center, that is, let's may call it delta 1, and if for the same beam, if I am applying say this load P2 over here, and say this is my deflected shape, and at the center again if I measure my delta 2 over here, what the principle of superposition states that your overall delta, this delta which was over here, must be equal to the summation of delta 1 plus delta 2, right? Essentially what I did, I just took this beam and I expressed it sort of a summation as these two separate loading conditions that I have over here, right? So this is the principle of superposition. Now let's go back, right? Let's go back to our world of stresses and strains, right? So we have this particular cube which has the sigma x's and the sigma y's and the sigma z's, right? So for this, how are we going to apply the principle of superposition and calculate the stresses and the strains? So to calculate the stresses and the strains, let's look at this figure now where I'm going to apply the principle of superposition, right? So I have the same cube, right? So this cube over here and the loading over here can be expressed simply in terms of, I can express this as my, and say this is my coordinate axis that I have over here, right? This is, say, my x, my vertically up is y, and this is my z, similar to here, sigma x along the x-axis, sigma y along the y-axis, and sigma z along the z-axis over here. If I'm expressing it like this, how I can express this combined loading over here as simply this is going to be in terms of sigma x over here, right? And it is going to be plus of, I am going to apply my sigma y, right, plus the third one, the only one that is left, right, that is my sigma z over here. Yeah. So essentially what I have done is that I have taken this one, right, and remember one very important thing in the principle of superposition is that at the when you take the combined loading and you break it up into the individual loadings, you must ensure that for each of these individual structures with these individual loadings, there must be an equilibrium, which it is in this case. I have taken sigma x, and if you multiply with the area and if we balance the forces, since it's, let's say it's a cube, right? It's the same dimensions everywhere. I'm going to balance the forces. Here also I balance the forces. Here also I balance the forces over here. I have taken this one and I'm blown up into 3 separate cubes with these individual loadings, the combined effect of which it is going to give my original loading over here, right? Now that I have these individual loadings, let me go back and try to write the different strains which are going to arise, right? So again, what I have over here are these 3 separate cases and the final case which has maybe all the loadings together, right? So let me take these individual cases as the first 3 cases and write out what I intend to find, right? So let me take the first case. So in the first case, I have the again my coordinate system. I'm going to draw it on the very right. I have x, y, and z over here, right? So if I have to go back, this is my first cube, sigma x over here, right? This is the next one is my second cube where I have sigma y, right? Then I have my third cube where I have my sigma z over here, and the fourth cube is the one in which all the stresses are acting. So let me go ahead and mark that as well. So in the fourth cube I have, of course, the sigma x, sigma y, I have sigma z and sigma z over here, right? So now I have these individual cases and a combined case which constitutes of all of these cases. What I'm trying to find is what are going to be my epsilon x, right? I have the stresses, I'm trying to find the strains. What is going to be my epsilon y and what is going to be my epsilon z, right? Let's look at the simple cases first. So in this one, for the first one, I know very well that my epsilon x simply from Hooke's law, remember the Hooke's law is sigma equals to E times epsilon. So epsilon x is simply going to be a positive of sigma x by E, right? Let me come to this block over here. Due to sigma y, my epsilon y is going to be positive of sigma y by E, right? Similarly, if I come to this block over here, this is going to be epsilon z is going to be positive of sigma z divided by E, right? Now, the question is that how do I fill in the other blocks which are there? Let's come over here, right? Go back to Poisson's ratio. What did we just discuss in that Poisson's ratio? Remember that bar which was just had the force or the stress along the x direction, along the other two direction, my epsilon y was what? My epsilon y was negative of nu epsilon x. Let's just go back and check once, right? Which we just figured over here. Right, my epsilon y was my negative of nu epsilon x. So let me just go back and fill up that cube or that matrix which I was trying to fill. My epsilon y over here is going to be negative of nu epsilon x, right, where epsilon x I have already written as sigma x divided by E. So I can sort of simplify this even further. I am going to write a negative of nu sigma x by E, right? In a very similar fashion, epsilon z over here now becomes negative of nu sigma x divided by E, right? Now, can you help me and try to fill up these different blocks of this particular matrix? Yes, you can, because now you know how to do it, right? Again, for this one, remember sigma y, sigma y. So what is going to be my epsilon x over here? Epsilon x, if you follow the analogical derivations which we are doing, epsilon x over here is simply going to be negative of nu sigma y divided by E. This one over here is also going to be negative of nu sigma y divided by E, right? Let's come to the last one over here. Here it is going to be for last one, meaning the where the stress is the sigma z. So this is going to be nu sigma z divided by E with a negative sign, and this one is also going to be negative of nu sigma z divided by E over here, right? So for these individual cubes, we have derived what are the strains along the three different directions are going to be. Now let's come back and look at my original cube which had the stresses in all the directions, right? So when I have all the directions, I am going to apply the principle of superposition over here. Here in this particular case, my epsilon x is simply going to be a summation of all of these three. Remember, this structure with these different stresses is simply a summation of these three structures that I have over here. So the strains, the epsilon x over here, I can come back and simply write that my epsilon x is going to be a positive of sigma x divided by E, which is the first term over here, negative of nu sigma y by E, right, and a negative of nu sigma z by E, right. Similarly, the other ones also are going to follow a very similar pattern, right? So in this particular case, my epsilon y is simply going to be, if I write this first and the others next, just to maintain a nice flow of expressions in the equations, it is going to be a positive sigma y by E, right, minus a negative of nu sigma x by E minus of nu sigma z by E over here. Similarly, the last one, if I have to write it, it is going to be positive of sigma z over E. Now you get a hang of it, of how to write it, right? And it's easy to remember once you sort of understand that how it works. It's easy to remember. Nu sigma y divided by E, right? I hope this is clear that how we derive this, right? Now, to give you a cleaner slide with the expressions properly written out, this is what we have. What we just derived over here is that for the generic case of loading, where we have the sigma x, sigma y, and the sigma z over here, these are the expressions that I get. And this is extremely important. This is the generalized Hookes law. But remember, under the case of the only axial loading, here in this figure I do not have shear yet. I only have axial. It's a triaxial, state of stress. You have the sigma x, sigma y, as well as the sigma z, right? So once you have this, so this is important. So this is the form of the generalized Hookes law in 3D when you have only the axial loading case. And you see the expressions are very easy to remember. If you are calculating epsilon x, it is going to be, of course, directly proportional as per the Hookes law, sigma x by E. Then you have a negative nu sigma y by E minus nu sigma z divided by E. And so on and so forth. The others will follow analogically a very similar pattern. Right now, that while we are still at the generalized Hookes law for axial, let me present to you a few of the other corollaries of this one, right? A few of the other extensions of the generalized Hookes law. One classic case of this is the concept of dilation. Dilation essentially means, suppose if you have a unit cube, right? Well, suppose you have a unit cube, it is just a change in volume. So if you say something is dilating, that essentially means that what is the change in volume that you have over here. And in these pages I have the expressions written out because we have already derived the basic formulations. If you just follow this one, this will be easy to understand. So what you have over here is a unit cube of dimension 1, 1, 1 about all the three directions. So and you are applying the stress sigma x, sigma y, and sigma z. Now once you have applied, since the original length is 1, the altered length is going to be 1 plus sigma x, 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon z. Why it is going to be like this? What is the change? Let's look at one particular direction. What is the change in length about x divided by the original length? Delta x divided by the original length was 1 equals to epsilon x. So I can simply write delta x equals to epsilon x, right? So that's why I can write the final length as 1 plus epsilon x, 1 plus epsilon y, and 1 plus epsilon z, right? So what is my change in volume? It is the final volume divided by the original volume. Final volume, as you can tell, is this expression over here, that the final length. So maybe I will probably just go ahead and mark it over here. So this is my final volume, right? And my original volume for a unit cube is 1, 1, 1, that is equals to 1 over here. Now, if you expand this one, it comes out to something like this. But remember that in this whole expression that we have, right, when you multiply this one, you will also get a term which is going to be your epsilon x times epsilon y times epsilon z, and the product of other smaller strains that you have. And since we are looking at very small strains, this can be ignored. So this particular guy is essentially what is written over here, that neglecting strain products, since that is small. You will get the individual strain products as well as epsilon x, epsilon y, epsilon z, right? So you see that this eventually boils down to this very simple relation, that your change in volume is simply the summation of the strains that you are getting, right? So here your E, that is the change in volume, it represents the change in volume per unit volume, because your original volume to begin with was 1, right? And this particular terminology and this particular expression, and this is just a definition, is known as dilation. So dilation is the change in volume per unit original volume that you had over here, right? Now if you have to take this expression over here, and you have to sort of tinker around and apply the formulas which we just derived. Essentially, you are trying to apply these expressions over here. If I remember the dilation, that came out as epsilon x plus epsilon y plus epsilon z over here. Now if you go ahead and substitute epsilon x, if you go ahead and substitute epsilon y and epsilon z, what you will essentially get is that an expression like this over here, your sigma x plus sigma y plus sigma z divided by the E minus the 2 nu. Why do you get the 2 nu? Because remember, if you just add these 3 over here, you have 2 places where you have nu sigma y by you have 1 over here and you have 1 over here. So that's why that every of these, the nu's times the stress divided by the E, has that 2 coefficient before that one, right? So just write it out, you will eventually get this particular formulation over here. And if you simplify this even further, what you eventually get, your dilation comes out to be this simple expression, that is 1 minus 2 nu divided by the Young's modulus E. Remember, the nu is the Poisson's ratio, so 1 minus 2 times the Poisson's ratio divided by the Young's modulus times the summation of the stresses across the different phases that you have, right? Going a bit further from here is that this is what we derived in the last page over here, that your E is something like this particular expression over here, 1 minus 2 times the Poisson's ratio divided by the Young's modulus times the sum of the stresses, right? Now if you are looking at a special case of a triaxial state of stress, that is the hydrostatic stress, which means that if you take this cube, or if you take a structure which is say deep underwater, it's in equilibrium, and essentially it has the same stresses acting in the x direction, in the y and in the z direction as well. So essentially, if you take this cube over here, this has the same stresses across all the directions, right? That you have sigma xa equals to, sorry, since it's a hydrostatic, the arrows will be in the other direction, because it's a compression, right? Once if you keep a body underwater, is going to be under compression. So let me erase this one, right? So what I'm going to have is these stresses equal and opposite along along all the directions that are there, right? So once you have these stresses which are acting, which are equal and opposite across all the stresses, all the phases, that is essentially if all of these are equal to your negative of sigma naught, right? All of them are equal hydrostatic stresses. So essentially, if you have something like this over here, and if you take this guy and if you substitute in this formulation, you get something like this. Does this look a little bit familiar of what you had learned in your +2 syllabus? Maybe it does. I can take this entire thing over here, and this particular expression that you have, that if I have to sort of separate this one out, that this 3 times 1 minus 2 nu divided by E that you get, if you take the reciprocal of that one over here, which is this particular formulation that you're looking at, right? Remember what this is called, the K, it is the bulk modulus, right? So we have this is related to the change in volume. Remember, we'll look at 3 different moduli, right? One was Young's modulus of elasticity, then we had looked at the shear modulus, or the modulus of rigidity, that was G, right? And this is the last one, this is the bulk modulus K, which is related to the change in volume. So the K is essentially nothing but my bulk modulus. So simply this expression at the very end of the day can be reduced to a very simple expression for my state of stress when you have a hydrostatic state of stress, that is a body which is underwater having the same sigma along all the directions. What you essentially get is that your dilation, that is the E, that is the change in volume divided by the original unit volume, is going to be a negative of the hydrostatic stress, that is the epsilon naught divided by the bulk modulus K, right? So I hope that you have understood or grasped the overall concept of the the 3D Hooke's law under just the axial case. What we are going to do next is we are going to spice it up a little bit more. We are also going to look at shear. So in addition to these sigma x, sigma y and the sigma z that you have, you are also going to have the shear forces across the different faces that you are going to get in this unit cube that you are looking at, right? So that comes up next.